on a nitrogen atom. So since they're on the atom, we can move them to a bond. So we could move them here and form a double bond between the nitrogen and the hydrogen. Is that allowed? No. Okay. How about we move them to the other spot? I would again have a double bond between nitrogen and hydrogen. Again, not allowed. I could move them all the way around to make a double bond between nitrogen and carbon. Am I allowed to have a double bond between nitrogen and carbon? So run into weird gray areas here. The question that's asked is going to run kind of contradictory to the thing that's shown up there. The question was asked, can I have a double bond between nitrogen and carbon? Yes, that is absolutely perfectly allowed. Okay? Between nitrogen and carbon. So those are things that are allowed to happen. Okay? But note, as we draw them, we also have to account for that bond, the other bonds appropriately. So in this particular drawing that we're looking at for our amine, is it allowed to have a double bond between the nitrogen and the carbon? No. Why not? You would exceed the octet on the carbon. So if we were going to try and do resonance, we don't have a way to do resonance with this particular nitrogen. Okay, so that's off the table. Whoops. Oh, that's not going to do what I want it to do. Okay. So what else could I do? So we're looking at the chemistry of that lone pair. What could it do?
Be a base or a nucleophile.
It could act as a base to donate electrons to H+, or it could act as a nucleophile to donate electrons to an electrophile. Does that make sense? Okay. What other chemistries do I have?
The nitrogen is more electronegative than carbon, so there's a partial positive and partial negative.
Cool. So where I would argue you're potentially going with that is that if we looked at the alcohol functional group, come on, why is my pen not working? Wow, it's really not working. I wonder if it's dead. Nope, it's not. Okay, we'll just talk through it. Is my finger gonna work? Pretend those are electrons. Okay, we could see the lone pair electrons on our oxygen potentially acting as a base or a nucleophile, but we could also talk about how a base could come through and we could remove the hydrogen. Right? Okay. Nitrogen, similar to oxygen, is electronegative. What base could remove that hydrogen? Okay, so there's a suggestion, OH. OH is our standard strong base, so if we try to go through and have OH come in and remove those electrons, what do we produce? What charge on the nitrogen? A negative. And then we'd have H2O. Is that a likely reaction to happen?
No,
No? Why not?
because oxygen would be better with the negative charge.
Oxygen is more stable than the nitrogen. Therefore, that reaction does not happen. It runs actually the reverse reaction, which means, are those hydrogens acidic? No. Okay. We could then push and say, well, what about nucleophiles? Could we have a nucleophile come in and potentially attack the carbon from underneath? And we're going to encounter similar issues. Okay. While that nitrogen is partially negative, and we do have the partial positives on both of those, both the hydrogen and the carbon, the nitrogen as a leaving group is bad because it would form a negative charge. Okay. The nitrogen as a conjugate base is equally bad. It's not electronegative enough or large enough to stabilize that negative charge, which means great observation on the partial positives, but they're effectively red herrings. What is the only chemistry available to the nitrogen? It's either a base or a nucleophile. That's it. So the amine functional group is actually kind of nice in that respect. The alcohol functional group, the oxygen, could do pretty much frickin' anything, okay, which made it very obnoxious to deal with different syntheses. If we think through the synthesis question that we worked through and was not recorded because it was on the exam, okay, the very first thing that we went through to do was convert the alcohol into the bromide. Why? Because the alcohol had access to a whole bunch of different chemistry that limited where I could navigate. As soon as we switch it to the bromide, the alkyl bromide, I really only have one chemistry available to me. That streamlines my process. Amines are nice in that respect. We've limited some of that chemistry and we're either base or nucleophile chemistry. Okay, and that's pretty much it. Okay, which is nice and not nice at the same time because that base chemistry is going to keep coming up and get irritating in almost every single one of our mechanisms whenever it shows up. Okay, and if you're like, well, screw OChem, it also shows up in biochem. Okay, so it's a really important functional group in the grand sense because you need that for biochem understanding as well, depending on the level of how your biochemistry class is taught. Okay? So within this week, you'll go through and look at some of the amine chemistry. Okay? Some of that showed up on the practice exam. Some of it actually showed up on this exam. Why? Because what did we just walk through? Was any of that new? No. All of that is an application of content you already know. Okay? So you should be able to apply that content across to help predict questions and navigate through it. Kind of, sort of? Other questions? You leave it to me. Again, wrong button. We have the ketone as a functional group. Okay. What did we say back in chapter 7 in OChem 1 that we needed to be aware of? We also had to be aware of enols. And enols, for better or worse, are tied to our ketones through that goofy word tautomerization. Right? How are these structures related? How are they different? What?
Not going back and forth, but more gas.
Yeah, they are related in that they can go back and forth. The question is, how are they going back and forth? So what we want to understand is, just like the synthesis, what are the changes that we're seeing between these structures that would allow us to decide how it could go back and forth? Okay, moving electrons, what'd you say? Location of the hydrogen. I only see one hydrogen in the enol. So I'm confused. Can you help clarify?
Gets pulled to the other part of the ring.
Okay, cool. I'm going to accept that, and I'm going to extra accept that because that was just vague enough so the rest of the class understand what he's talking about. I'm going to assume silence means no in this particular case. Okay? What makes this particularly challenging is that concept Remember that very first exam in OChem 1 where we reviewed the exam and you all were like, why did we get this question wrong? The number of pi and sigma bonds, and this doesn't make any sense. And I was like, well, let's draw in all the hydrogens. And everyone went, oh. You mean we had to count those when we count sigma and pi? Yeah, you had to count them. It was relevant to the overall question. Those are implied atoms that will come back and haunt you. And if we go through and add just a hair more detail, I'll only add the hydrogens where they are directly relevant. You should note that when we look from the ketone to the enol, that hydrogen has changed its location. Okay? I would argue we can't color code it as blue because we don't know that it is that hydrogen, and in fact it is probably not the same hydrogen. So when I asked the initial question, what are our relationships between these, hopefully what you noted was that we've changed the location of a hydrogen atom. We removed one and we placed one back on. Now that we know those changes, we can talk about how that happened. Other people noted that the electrons have moved around. We've got a pi bond in one spot and a pi bond in a different spot. 9 times out of 10, this is what students will try to do. Right? That curved arrow, we're going to move the pi bond there. Can you do that?
No.
Sure, why not? I just drew it. Why is that an invalid thing for me to do?
Because we have a positive oxygen and then a negative carbon.
Okay.
Carbon.
Negative carbon, I like that. So, no, I won't.
Well, your oxygen is still positive.
Okay. I'm generating a positive on the oxygen. So if I did those curved arrows, and for people copying along, that's okay, but please realize that literally what we are drawing is something horrendously wrong. Okay. I would argue still drawing is good because I want you to get used to the wrong path. Why is it wrong? We would get that positive oxygen, and then what else?
A negative hydrogen.
A negative hydrogen. Is that arrow push a good idea? No. We already answered this question earlier in the unit, or earlier today. How many times have we seen a positive oxygen? Never. And even then, when we did see them, did they at least have their octets? Yeah. This is an oxygen literally missing its octet. It only has 6 electrons, not the full complement of 8. Okay, lean into it more. H minus. How stable is H minus? It's charged. It is literally the smallest atom on our periodic table. When we consider organic chemistry, it's also the least electronegative-ish. Okay? There's no resonance. There's no other structure to help stabilize it. That is as unstable as you can possibly get. That should be screaming no frickin' way. Right? So instead of focusing on just moving the pi bond, what you should do is consider some more of the kind of chemistry that's happening within that structure. That chemistry does become challenging to manipulate. If we can't move that pi bond, well, actually, can we actually move that pi bond? Yeah? How? The first arrow we drew was saying, I want to move it down. I understand your logical flow on why you want to do that by looking at what shows up there at the product. But let's consider where those electrons started. Where are those electrons located? I'm blind. I can't see anything. Tell me where that line is in my structure. In between an oxygen and a carbon. Where do I want the electrons to move to? To the oxygen. Why? It's more electronegative. Does this arrow make sense right out of the gate? No. I don't even need to propagate what this draws out to be. It literally makes no sense. I'm moving electrons away from the electronegative element. Where would I rather those electrons move? So I could add this as a curved arrow. Right? I could even draw out a product on this. Am I done?
Positive and the negative charge.
I need the positive charge and the negative charge. If we understand our arrow flow, we can start to see where things move. What did I just draw? Oh, not an eraser. What did I just draw? I think it was mumbled over here. That's a resonance structure. This resonance structure can help us to see the chemistry in the underlying structure. If we now go through and look at the enol, where do I want my double bond to be? Which two carbons? Except the one with the alcohol and the one with the hydrogens, I would say cation and the one with the hydrogens. The cation doesn't have any electrons, so it can't make the double bond. There's no electrons for it to contribute. Where must the electrons come from? Which bond? The bond to the hydrogen. If I was to draw the result of that, I have to draw angle down a little bit. Screw it, I'm not going to do that. Move. What happened to the bond between that carbon and the hydrogen? It broke, which means there's my hydrogen. How is it connected to the structure?
The only one is.
It isn't, right? And another freaking eraser. And the other one would be. But I have H plus just appearing in the ether. Shouldn't something come along and remove that hydrogen from the structure? What would be something I could add to help that hydrogen come off? I could add a base. Depending on the base, I may see that charged, I may not. That's going to depend on what I've identified as the base. Do I now have my enol?
No.
No, what has to happen?
Oxygen needs to gain an H plus.
It needs to gain an H. Where could it gain the H from?
The one that just left? Or
We could go from the one that just left, okay? That is possible, but if we consider in the grand solution, there's probably lots of H bonded to something out there. It could pick it up from any one of those things. This now sets us up with our final product. Really all we've done is 2 mechanistic steps. That's it. The resonance we used to help us understand where the chemistry was, but that's it. We did 2 mechanistic steps. What were the 2 mechanistic steps we did?
elimination and acid base.
We did an elimination followed by an acid base. If we understand our fundamental reaction types, we can start to call up what those reagents are. Remember, for the elimination, we needed to break a hydrogen. We needed a leaving group. We didn't actually need a leaving group here. Or we could argue the leaving group was the pi bond on our structure. What did we do to eliminate? What did we need? Well, in elimination, typically what do you add?
Bases.
Base. What reagents do I need to add? I drew a base. So if I understand what's happening at each of those stages, I can start to call up some of the reagents naturally behind this. And what we've now just done is the tautomerization reaction going from a ketone to an enol under basic conditions. What we chose to focus on was that positive carbon in our resonance structure. Was there something else we could have focused on? That's not what was supposed to happen. Look at that resonance structure. I decided to uber focus in on stabilizing that positive carbon. Is there something else reactive in that structure that I could try to stabilize?
The negative
The negative oxygen. How could I stabilize that negative oxygen?
an acid.
I could give it an acid. I still have that carbocation. How could I stabilize that carbocation?
Elimination is
An elimination to remove one of those hydrogens. What's going to help remove that hydrogen?
in a base, but
Oh, awesome. I was wondering if that's why there was a hesitation there. You're like, a base would remove that hydrogen, but what?
more acidic.
We just said it was under acidic conditions, which means whatever's going to remove that can't be a strong base. It could still be a weak base. It could be our solvent. And where do we end? The exact same place. So we can run this mechanism either under acidic conditions or under basic conditions, depending on the environment that we either choose or the environment that is forced upon us by the question state. As we navigate it, we need to see certain things start to appear. The resonance gets a little bit questionable to draw our structures from, because resonance, when we draw our structures, we should always draw them as the most stable structure. So when we're considering our mechanism, while that resonance is useful to us, our mechanism more appropriately looks like this. Okay? And if you wanted to get extra nuanced, you can. We can say our pi bond picks up that hydrogen. What happens in the top case? Our base, as a negative, comes in and picks it up. So hopefully what we see is under acidic conditions, what charges start to appear?
Positive.
Positives. And under basic conditions, what do we start to see?
More negative.
We see the negatives. So if we understand those charged states, we can help to explain and come up with a mechanism that more appropriately describes the actual energetics of our system. Kind of, sort of? Does that all make sense? Do you have questions? We'll leave that kind of on there as a hint. What's different about this ketone?
We have a possible carbocation ion on the tertiary. So like one side would be this, where the chemistry would be at.
When we looked at that ketone, when we did the keto-enol tautomerization, did we ever talk about that carbon being a cation?
No.
No. Okay. So I understand where you're going with that. It's tertiary, so a carbocation could potentially form there. Okay. But let's shift our focus back to that ketone. What makes this red ketone different than the black ketone? It's not symmetric, which you have actually already drawn in your notes because you went through and specified the difference in the hydrogens. Fantastic. Right? Because it is not symmetric, what does that mean could possibly happen when we look at our enols? We could get two different enols. Okay? And what we're going to shift to is a new name, which we'll show you in just a second. Enol 1 versus enol 2. These aren't technically enols. Why? There's no hydrogen. Okay, that's it. We removed that hydrogen entirely. These are what are technically known as enolates. All we did was remove that hydrogen. So we're forming these under basic conditions, not under acidic conditions. We know that because we're seeing that negative charge. Under acidic conditions, you're going to get similar issues coming up, but the enolates add some extra pizzazz that we can play around with. How would we choose which one we got? Or do we get them both? And if we get them both, do we get them in different ratios or the same ratio?
The enolate's the final product, or is it the intermediate?
The enolate is technically an intermediate, but this enolate is what's going to dictate your chemistry moving forwards. So when you continue to react this out, you could see a mixture of products depending on the ratio between those two enolates. So instead of focusing on all the secondary chemistry, let's just drop it here.
So then you decide which one is more likely?
Yeah, which one's more likely? How would we decide which one's more likely?
Resonance,
Maybe
stability.
the first one is because of that carbocation, which I hesitate to say because you said it wasn't important.
Okay.
I feel like it was.
So let's lean into the resonance, because this is going to go back to you saying carbocation, why we put the question mark, and you're seeing that, oh, carbocation. What's the most reactive thing in both these structures? The negative oxygen, which means we need to stabilize that negative oxygen. What are we going to do with those electrons?
Move them to, or bring them down for a double bond.
Bring them down to make a double bond. What happens at the next carbon?
That double bond needs to move to.
The carbon, yeah. Just
Whoa, too many. And then I erased all sorts of other things. What charge builds on that carbon?
Negative.
Ooh, what charge?
Negative. So it's a positive.
Not a positive. Interesting.
So is the negative more stable in the secondary carbon?
Okay, so we could try to evaluate the structure from there. Again, how are you going to decide which one you get?
I mean, can we just use different bases to get a different hydrogen to be moved?
Cool, using different bases will preference one or the other. But before we can get into what base preferences one or the other, you've still got to decide what's your difference between these.
The bottom one has a more. I mean, we're looking at the oxygen, right?
And this is where I think this becomes challenging to evaluate. Which of these two structures is the structure you should be considering, quote unquote, the most? The left structures or the right structures? Why the left structures? Cool, those are the most stable. We're now introducing concepts of stability. Have we talked about concepts of stability before, particularly when we're getting two different products? Yes, and what did we evaluate? Or terms, language that we use when we were looking at this? Kinetic versus thermodynamic. So if we're going to look at these two now as our most stable, okay, are more likely, what we're now going to decide is, can I tell a thermodynamic difference between them? Because that's stability. Kinetics is all about what the reaction mechanism is doing. I didn't draw a mechanism yet, so we don't know. But we can look at the thermodynamics. What's the difference between those two?
Just the placement of the pi bond.
Placement of the pi bond. There was someone else dropping a term. The substitution pattern of the pi bond. And the more substituted our pi bond is, the more stable it is, which means
The purple is more stable.
we have a thermo product up top.
Is that because, like, I know it forms the negative on the tertiary carbon?
Nope,
but-
nope,
No.
nope, nope. Look in the black box.
Okay.
There is no negative on a tertiary carbon. What makes that thermodynamic product the most stable is you have the most substituted double bond. Period. That's it.
So we don't think about the resonance over there for the
You don't need to worry about the resonance when determining the thermodynamic. When should you worry about the resonance?
Maybe when you're trying to see what happens next.
Yeah, but it's thermodynamic and
Okay.
kinetic. If I want to figure out which one's the kinetic product, what should I potentially look at? The reaction mechanism, and ultimately the reaction mechanism is talking about how I removed a hydrogen. A hydrogen located either here for the purple or here for our blue. Which one of those do I think would be faster to remove? The blue, why? It's on the outside, it's more accessible, which means the blue one is And funnily enough, if we looked at our resonance structure, the more stable anion is our kinetic product. So when we're now trying to decide which one do I get, kinetic or thermodynamic, this is where we can pull back the same content that we had before. We can play with temperatures. Right? We can play with temperature and time. Colder temperatures are going to favor our kinetic. Warmer temperatures are going to favor our thermodynamic. Shorter times favor kinetic. Longer times favor thermodynamic. Okay? But as Andrew was wise enough to point out, we also now introduce the concept of different base strengths. And you go, well, hydroxide was a strong base. It turns out, while hydroxide is a strong base, it's not that strong. And in the grand scheme of organic chemistry, we have significantly stronger bases. Why does that matter? Those stronger bases are going to now preference one versus the other of our potential products. So we could look at the strength of the bases to determine which of our structures is more likely to form. This means when I carry the reaction on, it's because I was trying to say, I could see substitution happen at different spots. I've got, in my resonance, a good nucleophile. If I form the thermodynamic product, my nucleophile substitution is going to happen at that tertiary position. If I'm running under kinetic conditions, I'm going to get it happening at that second. So I now have to pay attention to the symmetry or lack of symmetry when dealing with our enolates. Hooray. Okay. And I would ask if you want more, but we're done.